So in the introduction to vibrational motion, we looked at an object vibrating on the end of a spring. In this video, we're going to start with pendulums. And a simple pendulum consists of an object at the end of a long string, which we assume to be massless. So here is the equilibrium position of the pendulum, and it swings back and forth between its maximum displacements, or the amplitude. And for a pendulum, the displacement is measured in terms of this arc length of the path. So the restoring force is no longer a spring, but the restoring force is actually provided by gravity. So here you can see a force diagram of all the forces acting on the object. So we have the tension force from the string, and then the gravity force. So part of the gravity force and the tension force are always perpendicular to the path of the string. So these forces, since they're perpendicular to the object's displacement, do not do any work on the object. Instead, they provide the centripetal force to keep this object moving in sort of a circle. So the part that actually changes the object's acceleration is going to be this part of the gravity, which is parallel to the object's displacement, or in other words, tangential to the object's path. So the tangential component of gravity serves as the restoring force in the pendulum. And instead of elastic energy and kinetic energy, the total energy of a pendulum system transfers between gravitational potential energy and kinetic energy. And the period of a pendulum, instead of the force constant and the mass of the object, the period of a pendulum depends on the length of the string and the gravitational acceleration, g, which is 9.8 on the Earth's surface. So the period is 2 pi square root L divided by g, and then the frequency is just the reciprocal of that. So again, this expression makes sense because if the gravitational acceleration is higher, then there's more gravity, so the object swings down faster from the max displacement to the equilibrium position. So since it swings down faster, the frequency should be higher. Whereas if the length of the string is longer, then it makes sense that the frequency would be lower. So in the simple pendulum and the spring systems, we've ignored friction, so the vibrational motion basically continues forever, and it always goes to the same amplitude each cycle. So when there's friction in a vibrational system, the amplitude and frequency actually decrease with time due to the friction. And this process is called damping. So based on the amount of friction in the system, there are 3 basic types of damped systems. The first is a weakly damped system. So this is the most mild, where the amplitude and frequency just slowly decrease with time. In an overdamped system, most of the elastic energy of the stretch system, as it moves to equilibrium, most of this energy is converted into internal energy, such as heat. So as a result, the object does not have much kinetic energy, so it moves very slowly back to equilibrium. In a critically damped system, the object quickly returns to equilibrium, but it does not overshoot the equilibrium position, so the vibration does not continue once it reaches equilibrium for the first time. So what if we want to make the vibrations continue, even if there's some damping going on? Well, in that case, we can exert an external force on the vibrating object. But it turns out that there's a special condition if we want to actually increase the amplitude of the vibration and keep it going. So, for example, if this kid is swinging, you can't just push him randomly, because if you just do that, then you could end up pushing him when he's on his way down, and then you'll just stop him. So you have to push him in a special pattern. So resonance is something that occurs when an external force is exerted on a vibrating object at a frequency similar to that of the frequency of the vibrations. So when that occurs, the amplitude of the vibration increases. So for example, if this kid is swinging and he passes the equilibrium position on his way up every 1.5 seconds. So let's say you push him not randomly, but every 1.5 seconds, right when he's on this bottom position on the way up. When you do that, the frequency of your pushing and the frequency of his swinging are the same, so resonance occurs, and the amplitude of his swinging will increase.